My name is Mirek Franc. I work at SUSE in the kernel core team, and I prepared this talk about SECCOMP. I just want to clarify that I don't have any upstream contributions to SECCOMP whatsoever, but I was asked by my boss basically to look into it, to figure out how it works so that we can backport patches to SUSE kernel. This is kind of a teaser slide, You will all know the utility called file, right? It's basically this program that you execute on the command line. It reads contents of some file. And it reads the content, and based on some magic numbers, it will basically tell you what the file contains, right? And now, when you run this under Valgrind, it ends up like this. It tells you like bad syscall. And at the end of the talk, you will understand why it happens. It's basically because of SECCOMP. And I have a proposed solution for this kind of problem. So what is SECCOMP? First, SECCOMP is short for secure computing. It has nothing to do with confidential computing or secure execution or secure boot whatsoever. It's basically a feature of the Linux kernel, and it implements one software engineering pattern, let's say, that is called sandboxing. You have like many things like browsers, emulators, containers and stuff, and they execute like untrusted code, or they analyze untrusted data. And somebody might write an exploit and hijack the execution. But SECCOMP kind of helps with this, because basically with SECCOMP you promise kernel not execute certain syscall numbers. You all know what syscall is, right? So you promise kernel not to execute certain syscalls or certain syscalls with certain arguments at the beginning, But when you break that promise, afterwards, you are basically killed by kernel. That's basically what it does in short, We all know we should write like secure code and maybe write stuff in Rust or whatsoever, but the reality is there will always be like exploits. So this is like an extremely useful feature, and it's basically everywhere, If you have your Android phone, basically every application is sandboxed this way, Yeah, this is kind of conceptually how it works, You run a file, and that file utility at the very beginning, it says SECCOMP's, it calls SECCOMP syscall, because SECCOMP is just another syscall. And it tells kernel ban ptrace, Kernel says OK. But then a file reads some data, and maybe it's exploited, because you fetch some random stuff from the internet. And then that exploit tries to call ptrace. But at that point, kernel says, but a file promised me it will never call ptrace. So it kills the file, the process. Does it make sense? Perfect. Is it? Yeah, this is like a SECCOMP history. Sorry, I need to drink a bit. Like this file is kind of packed. But basically, what I want you to remember is basically there are 3 major versions of SECCOMP. SECCOMP was started in 2005. I think it was Andrea Arcangeli who introduced it into Linux kernel. And the original version it was basically only Boolean flag. You could only turn it on, and then it stayed on. And it's called, it's still available, it's called strict mode. And it basically allows the program from that moment to execute only those four, I cannot point it, those four syscalls: read, write, exit, and seek return. And if a program executes anything else, it will be killed by, it will be delivered SECCOMP, basically. And this kind of already is broken currently, right? Because as a user space programmer, you don't always have like a control over which syscalls you execute, right? You calling, I know, some glibc stuff, and glibc stuff does calls some random syscalls, and you don't even know it, And at some point, actually, glibc broke this model because it started calling exit group, like instead of exit, even for like single-threaded simple programs, So if you like have empty main, you exit from main, and glibc will, if you link your program with glibc, it will just call exit group, So at that point it is killed. Maybe at that point it doesn't matter anymore, but it's kind of useless, So there comes year 2012. And SECCOMP actually got extension. I apologize, I need to drink some more water. SECCOMP mode filter was introduced. And SECCOMP mode filter is kind of, it got additional parameter. And that parameter, basically, you can pass CBPF program, And that I will show you on later slides, That CBPF program basically decides like which syscalls and which arguments are either like allowed or disallowed, And then in the latest version in kernel 5, 2019, it got another extension, and those are like a user space notification. Basically, it's used in containers. When you have like several user space programs, and you have some basically supervising programs, and you have some containers. And it basically allows like that container to kind of install SECCOMP filter and get a descriptor. And it passes that descriptor to another supervising programs. And when that container like executes some syscall, the supervising program is notified and basically can decide what should happen. So instead of kernel deciding it, some other user space program decides what happens when you execute some syscall or some combination of arguments, So those are three major versions that are like still available now, and I have some details on the slides. You can read it later. Now back to that second version of SECCOMP, the SECCOMP mode filter. Like what is actually BPF, right? It's not. Please do not confuse it with eBPF, which is kind of extended version, This is a bit simple. BPF stands for basic BSD packet filter, It's almost as old as Linux kernel, and it basically dates back to 1992. And sometimes it's called CBPF to like differentiate it from eBPF, And it's a basically simple instruction set, extremely simplified. You have 2 registers only, and you have 64-bit instructions. 16-bit is opcode, 2 8-bit jump offset, and one immediate field, and you have load, store, jump, return, arithmetic instructions and stuff. What is important here is how it looks, This I have an example of CBPF program. It's basically, I need to point out that this is not how you actually write CBPF programs. This is just a conceptual example, because there's no compiler that targets this thing. So you have like 4 lines. You in that CBPF program, you kind of load syscall number, or you load syscall argument, and then you, in this case, it's a syscall number. You compare that syscall number with a number of syscall you care about, in this case, bit arrays, If it's equal, then you jump at label L1. If it's not equal, you jump at label L2, So if the programs call bit arrays, it's killed, otherwise it's allowed to continue. And I have like a complete or almost complete C example, This is kind of hello world of SECCOMP, I don't have like includes here, but you can find them in the man page, So this is like how you could use it, with just glibc headers. It contains these 4 parts, The first structure, SOC filter, is basically, this is the BPF program. It's similar that I showed you on previous slide. This is basically these 4 lines, except that instead of bit arrays, I'm banning alarm syscall. So this is how you actually write like CBPF programs. It's with C macros. So first line is basically fetching of syscall number. That's track SECCOMP data. That is handed by a kernel to the CBPF program, So you have available like syscall number, architecture magic number, syscall arguments. So now you compare it with the number you care about, in this case alarm, and you jump either at 3rd line or 4th line, So either if the syscall number is equal to alarm, you kill yourself, otherwise you are allowed to continue. Now I compute the length of the program, and the third thing that PRCTL call is basically I need to promise kernel first that I'll be not gaining new privileges, because otherwise I would be allowed to kind of escape the sandboxing. If I didn't do this, the last thing, the 4th syscall, actual SECCOMP syscall would fail. So that yeah. And if I do those 4 things, last thing I install like a SECCOMP filter. I passed that program structure. And now I'm basically sandboxed. And if I call alarm from now on, I will be killed. That's basically how it works. This is kind of hello world, how you do it. Of course, this is kind of, it's a lot of code for a simple thing, right? And there's actually like a library called libseccomp that has a C and Python interface that allows you to write this kind of in a nicer way. So I recommend, if you're planning to use SECCOMP for user space programming, that you kind of check it out. Now, back to Valgrind. I don't know how many people actually know what Valgrind is, but the proper way to say it is that Valgrind is a kind of tool for creating other tools for dynamic binary analysis. Most people who use Valgrind actually are only familiar with memcheck, which kind of helps you debug like memory issues, but there are other tools. You can call Valgrind it -- tool equals something, you know, and you can debug some, you can profile your heap, or you can debug some threading issues, and there are like multiple tools, you know. If you are not familiar with it, I recommend to check it out. But the important part, and why I'm talking about this, is basically how Valgrind itself works, you know. Basically, Valgrind, when you run it, for example, on that file utility, it's just read that file utility, and it reads all the libraries that utility uses. It decompiles that code into some intermediate representation. It instruments that intermediate representations and compiles it back and stores it in some memory buffer and execute it from the buffer. So basically, Valgrind and tool being debugged are a single process, you know. And now, like what happened on that first slide, basically on that teaser slide, if you remember from the very beginning, you know, you run a user bin file on with Valgrind, right? And that user bin file called SECCOMP syscall because it wanted to be sandboxed. But of course, there's a problem because Valgrind currently doesn't implement SECCOMP syscall, so it just dies, you know. And the reason why Valgrind needs to handle like syscalls specifically is that basically that's the only point where Valgrind kind of loses control, because Valgrind emulates the entire userland, you know. But when you are calling a syscall, you are escaping into kernel. And it actually needs to sanitize input and outputs from the syscalls. You know, for example, when you syscalls returns you some data, Valgrind, for example, must mark that data as that memory as initialized, you know, so that, for example, memcheck could do its duties, you know. So yeah, so that's how it works. And now my proposed solution for how to fix this thing. This is kind of example how you can implement like a syscall in Valgrind. This is probably really outdated because I don't think that kernel implements like time syscall, but these days it's probably some virtual syscall. But this is just an example. You have pre-wrapper when you sanitize inputs to the syscall, and you have post-wrapper when you sanitize outputs, you know. Some syscalls don't need post-wrapper, but they all need pre-wrapper. So this is just an example. My actual SECCOMP patch is actually quite longer. It wouldn't fit on the slide, so this is... do you have any questions about this? Otherwise, I will go on. Yeah, and you... Then, when you write these wrappers, you can actually like you need to plug them in. This is how you do it. It's extremely simple, you know. So I think anybody could implement another syscall into Valgrind. Actually, the trouble with Valgrind is that many syscalls are actually not implemented. So you write Valgrind on some binary and it fails because the syscall is not implemented. Because not all syscalls are called too often. You know, you have some weird syscalls like a reboot. You know, you call once in a few hours, and then you have read write that are executed constantly. You know, so common syscalls are usually implemented. More obscure syscalls are not. So we need to do this. You know, now what happens is basically it turns out. We didn't help ourselves much, right? Because okay, we implemented, say, this SECCOMP syscall, you know, instead of that time I had on the slide. And what happens is that okay, you run a file under Valgrind, and file calls SECCOMP to sandbox itself. Okay, Valgrind sanitizes inputs, pass the syscall to the kernel, and kernel says okay. And now, like we are sandboxed, and say we that SECCOMP syscall actually implemented filter that ban like a get PID syscall. Because user bin file probably doesn't need to call get PID, but Valgrind does, and the file and Valgrind are now one process. So Valgrind, on his own behalf, calls get PID and gets killed by the kernel. So that's a bit unfortunate situation because like Valgrind itself is sandboxed. But that sandboxing is decided by the program Valgrind tries to analyze. Does it make sense? Perfect. Okay, so I proposing to implement this feature. And that is, I would like to hide it under this flag here on Valgrind. SECCOMP disable yes at the top of the slide. And basically what happens is that I like implement SECCOMP syscall in Valgrind, and I'm gonna just pretend it succeeded. I will never pass it to the kernel. So you run the user bin file under Valgrind. User bin file calls SECCOMP, and Valgrind will just pretend that it happened without actually passing it to the kernel. So user bin file thinks it's sandboxed, but it's actually not. And then Valgrind can call get PID, and that at the beginning, that problem that happened never happens. You know. Of course, this is a bit a problem, right? Because from security standpoint. But I think it's not such a huge problem because you usually don't run Valgrind in production. You run it when you are debugging stuff. But I still think it's a good idea not to do it by default and hide it under some flag, you know. So yeah, now. Back to the teaser slide. Now I run Valgrind with disable SECCOMP yes, and now it works, you know, because file tried to sandbox Valgrind, but it was not successful, so execution can proceed. This is useful because, you know, some programs actually so say QEMU allows sandboxing with SECCOMP. And they have some flag that allow you to turn it on and off dynamically. But some programs like file don't. So this is useful to allow Valgrind to turn it so that you need to recompile say file utility, because file utility allows to turn off SECCOMP only during compilation. But this way you don't need to recompile file, you can run it and it just works. Yeah, this is basically what I was talking about, that some programs don't allow to switch off SECCOMP dynamically. And Valgrind is, I know these days we have, say, sanitizers, right? but sanitizers require a compilation, and sometimes you don't have like option to recompile your program with sanitizers, and sometimes you cannot even. You have some binary blobs, and you need to like analyze them. Okay, so that's it. Of course, security concerns, you know. First, it's not meant to be default. So, and second, it's again, you know, you'll not run it on production. So I think that it will be a useful feature for Valgrind. Of course, there are some alternatives to this, like, for example, one idea I gathered from somebody is that we could solve it a bit differently. We could, when writing that prev wrapper in Valgrind, we could like gather all the syscalls that Valgrind needs at the beginning, build a CBPF program that allows them, and prepend it to the like CBPF program that the program being analyzed kind of passes to the kernel and pass it to the kernel. Then it would like, we wouldn't have this problem, right? That Valgrind executes certain syscall that original like program like didn't allow. But it's kind of confusing, and now we have like kind of partial sandboxing. And it will be extremely confusing to the users, right? And it will be kind of not really transparent, and it's better not to do it. It's better to just turn sandboxing on and off. Another thing we could do, we could implement, because CBPF like execution is implemented in kernel, you know, so we could actually implement it in Valgrind. We could write it a prev wrapper, SECCOMP prev wrapper, and implement like BPF interpreter, and do these like implement this sandboxing in the Valgrind itself. But obviously, this will be a lot more complicated first, and it will also kind of, you're still like doing this in user space, and Valgrind and program being analyzed are one process. So if you like hijack like the program, you can hijack also Valgrind. Like kernel is better to, from security standpoint, it's better to doing this enforcing. So yeah, I think it's not a good idea either, no. And that's basically end of my talk. Here are some like slides if you want to read them. And yeah, that's basically end of my talk. So do you have some questions or concerns? Thank you for being patient with me. I apologize for the delay.